see if we can make this work. So I'm going to talk about, not talk about lock picking. So the first kind of disappointment is that if you're here to talk about lock picking, you probably have some time to go down to Starbucks and play with their wireless network or whatever. I'm getting old. I mean, this is one of the properties of being an old school hacker from the old days, is that as you get older, you discover that hacking your body is a little bit harder than hacking computers. And in particular, I find that I'm getting less and less good at picking locks. But to make up for that, I've been thinking about locks for a while. And one of the things that I do in my day job is I'm a cryptographer and computing systems security person. And one of the things that I thought about a couple of years ago is the question of, can you think about locks and physical security using the same mindset that we think about computers and cryptography with? And the answer is you can. And in fact, the purpose of my talk is that if you are interested in locks and physical security and you're a computer scientist, you actually have a really big advantage compared with thinking about these things in mechanical terms. So I'm going to talk about picking locks using cryptography. In particular, one of the things is, we're computer scientists, right? The kind of core people here got their introduction to technology through computers. And the question is, why should those of us who are really good at thinking about computers waste our time thinking about these little mechanical, very primitive, kind of 19th century technology? And one of the things is that, first of all, you can think about them in the same terms, and over the last 100 years or so, in particular, since they invented computers, the people responsible for thinking about physical security, the locksmiths and the safe manufacturers and so on, have gone from thinking about these things in very scientific, open terms to becoming very insular and private. And in fact, they've stopped being critical about security in the same way that we think about security. We tend to be very critical. We say, well, let's look for the flaw. The physical security community, by and large, says, well, if somebody finds a flaw, the problem is these people trying to find flaws, not the flaw itself. This idea of independent analysis has kind of gone away from the physical security world. So we all know what physical security is. We all know what locks are. There are two major categories of locking mechanisms. There are combination locks, the kind used on cheap padlocks and to protect safes. I'm not going to be talking about those here. There are keyed locks, where you take a physical token and put it in the lock, and the physical token kind of convinces the lock to open in some way. That's the kind that I'm going to talk about. Now, it's interesting that even this language is something that's familiar to computer scientists, right? We talk about keys, cryptographic keys and things like that. We talk about people who break into computer systems. We talk about them as being intruders. These are all, they're not breaking into anything and they're not intruding on anything in any physical sense. The language of computer science, again, is taken right out of that physical locksmithing world. So it's also possible that we can learn something by studying these things a little more. Okay, so the kind of lock that's most familiar to everybody is called the pin tumbler lock. Now, this is the picture of the user interface of a pin tumbler lock. How many of you have ever operated a door? Okay. So this user interface is fairly familiar, even though, on it itself, from the way a computer scientist would look at this, they'd say, this is a terrible user interface. There are no pop-up windows. Nothing's labeled. There's no help. So the components of this user interface are really three important parts. There's the shell, which is the part of the lock that's fixed to the door or the container. The plug, which is the part that rotates and that operates the locking mechanism. And the keyway slot, and that's kind of the user interface for the lock where you insert the key. And if you kind of look through the user interface, you don't really see much. You might be able to see a little pin there but you don't get too much of a hint as to what's actually going on inside the lock. So what's going on inside is kind of the interesting question. The boundary between the shell, the part that's fixed to the door, and the plug, the part that rotates, is called the shear line for the shear force that's created. And that's really where all the action is from a security point of view. So what keeps the plug from rotating when there's no key in? Well, there are a set of pins, or more properly, they're called pin stacks, that protrude out of holes in the shell and go into holes in the plug that keep the plug from rotating. What the key does is lifts those pins to a particular height where the pin is cut. And if the key lifts all of the cuts up to the shear line, then the plug can rotate. So it's a little mechanical computer that tests keys to see whether or not the key knows the secret height to lift each of the pins to. So if we took a lock and looked at it from the side and cut it apart with a milling machine, how many of you have a milling machine? Okay, more of you should have a milling machine, particularly if you're interested in physical security hacking. So now we're looking at that lock cylinder from the side. You can see this has 6 little pin stacks. Here's the shell, here's the plug, this boundary here is the shear line, and these are the pins, and each of these pins you can see has a little cut in it. The key goes in from the front, and the little wobbly pieces on the key lift these cuts up, if it's a correct key, all of them to the shear line, and it lets the plug rotate. So that's how this little analog mechanical computer works to test keys. And again, I'm talking about this in kind of computing terms. I'm thinking of the function of a lock is as a little key testing machine. So how do the keys work? So here's some locksmithing terminology if you want to impress a locksmith, or more likely make a locksmith really suspicious of your intentions. The surface of the key where the little notches are cut that lift the pins up to a particular height is called the bidding surface, or the bidding of the key. And the notch height, the height of the key at any particular pin position, is the inverse of the corresponding depth of the cut, right? So a correct key is going to correspond to, in its height to the height of that cut inside the lock. So if you talk about the bidding of the key, that's just a list of all of the heights that the key is cut to at each of the individual pin position. Now, even though a lock looks kind of like an analog device, in fact, it's really digital in the sense that a lockmaker is typically going to use a fixed number of different heights that a key might be cut to. There might be somewhere between 5 and 10 possible heights that a key might be cut to. So you can kind of get a complete description of a key by knowing what kind of lock it fits in and the complete list of the heights that it's been cut to. So here's an example of a key, and this is a key of type SC20 that's conveniently printed on the key. And here's its bidding surface, and here are the cuts. So the first cut here is cut to this depth, cut number 3. Then it's a little higher. Here's cut number 1. You can see that's a little higher up than cut number 3. Then there's 4, a 1, a 5, and here's a really deep cut, a 9. So this is cut 314159. So this is pi. So a complete description. You could get a duplicate of this key by walking into a locksmith and saying, I need an SC20 key cut to 314159, and they would be able to cut it to these specifications, and it would work in the same lock as this one. So now we've got a kind of concise way of thinking about and describing keys, and that's going to turn out to be very useful to us later. So when we stick that correct key into the lock, that will make all of these cuts line up at the shear line, and now we can rotate the plug and it will operate the lock. If you put a wrong key in, it might line some of the cuts up at the shear line, but as long as at least one is in the wrong place, the lock is going to, from the user's point of view, not operate at all. So one of the important properties of these locks is that if the lock is a perfectly designed lock, if there's no mechanical imperfection, a slightly wrong key is the same from the user's point of view as a completely wrong key. And only the exactly correct one will operate the lock at all. And that turns out not to be true, but I'm going to assume it's true. I'm going to give the lock maker really the benefit of the doubt and still attack locks. So what if you wanted to attack a lock? How might you think about it? So there's some attacks that just bypass the lock completely, right? So getting an unauthorized duplicate of a key is an example, where you're not attacking the lock itself, you're just getting a copy of the key. Or you might bypass the lock, right? You might go in through the window, or stick something under the door to turn the knob from the inside, or something like that. There are other attacks against locks that you might have to worry about that depend on weaknesses in the lock's implementation. So they depend essentially on the manufacturing process having bugs in it. So examples of weaknesses that depend on the lock being manufactured poorly are things like lockpicking, vulnerability to lockpicking, or vulnerability to brute force, which in locks means applying brute force. And in computers it means something else. But there are other attacks that are based on design weaknesses. And what I mean by a design weakness is even if the lock is manufactured absolutely perfectly, even if physics is really nice to the lock and prevents there from being any mechanical imperfections, and anything that's round is actually really round, and anything that's a particular height is really that height, you're still going to have a flaw. And that's the kind of attack that I'm going to be focusing on here. So one question is, what about brute force? How secure are locks if you want to try all the keys? Well, there are two parameters. One is the number of pins in it, the number of tumblers in the lock, and the other is the number of different cut depths that it might be used to. And basically, the maximum number of keys that a lock might have is the number of cut depths raised to the power of the number of pin stacks. And that's exponential, in other words, in the number of pin stacks. And there are a couple of little factors that reduce that slightly, but basically that's pretty close to the number. So it's exponential in the number of pin stacks. A computer scientist would say that's great news. But on the other hand, there aren't really that many pin stacks and that many cut depths, so the bottom line is that there are somewhere between about 250 and 10 million different keys for a given lock design. Now, the computer scientist in you would say, yeah, but my Pentium 4 can go through 10 million keys in under a second, so obviously that's insecure. But remember that you have to try these keys one at a time, and testing 10 million keys or even only 250 keys is going to take a while. So that's probably not a very good attack against locks. So we might have to be a little more clever than that. So let's see. Barry will talk about lockpicking. So let's go back to computer science here for a second. So one of the useful principles from computer science, from computer security, is to separate out thinking about the design from thinking about the implementation. In other words, you think about what the thing is supposed to be doing and think about whether that's secure. And if that's not secure, it doesn't matter how good a job the programmer does, because even if it's perfect, you're still going to have a weakness. In fact, if it's imperfect, maybe the imperfection will cancel out the weakness. So, thinking about the design first is a useful kind of computer science way of thinking about this. There's another computer science principle, and this is a principle from somewhat advanced cryptography, is to remember that some kinds of security systems are easy to analyze by thinking about some components as what we call oracles. And basically, an oracle is something that you're not allowed to look inside of, but that the attacker is allowed to use through the normal interface. So there's a user interface, and that will tell you whether you guessed right about something. And an example of an oracle is like logging in online. That's an oracle for testing somebody's password, right? You can log in over the network, try their password, and the computer will act as an oracle, telling you whether or not that was the right password. Well, a lock is an oracle. It tells you whether or not you've got the right key. So maybe we can think about these in those terms. So a question, as soon as you have a system that has an oracle in it, the computer scientist in you should ask two questions, two really important questions. First of all, what does it cost the attacker to ask the oracle a question? How long does it take? What are the resources for the attacker to ask a question? So how many questions can you expect the attacker to maybe be able to ask? And can they structure queries to the oracle in a way that lets them learn something they're not supposed to be able to know? Right? You think the oracle only tells you whether or not one key is valid, but maybe the oracle will tell you something more interesting about the key that you didn't think the attacker should be able to learn. So here's an example of, again, this is computer science, not locksmithing, but here's an example of a way of testing whether a password is valid. So you have a little loop. This is kind of pseudo C. So, go up to the length of the password, get the next character, compare the character to the password. If the character is the wrong character at that position of the password, return bad password, otherwise print out the message bad password, otherwise go and get the next character. Is this a good way of testing passwords? No. Why is it a bad way of testing passwords? So what can you do? Instead of having to test the whole password, you can test the password how? One character at a time. So instead of having to submit the whole password, you can find out, is the first character of the password A? If not, is it B? Is it C? Ah, it's C. What's the next character? And so on. So this is a really bad program to write for testing passwords in an online system. So one question is, what went wrong here? Well, in more formal terms, right, in kind of mathematical terms, what we'd expect is that the cost of an exhaustive search should be exponential with the length of the password. It should be the number of characters raised to the power of the length of the password. But here, it's only the number of characters in the password times the number of possible characters, which is much smaller. So the standard fix to this problem, right, first of all, you'd fire the programmer who wrote that program.